Hello, sir. Am I audible?
Yeah, audible.
Sir, few of us want to change our elective to this course. So when the course adjustment period will open, can we put a request?
Yeah, we can put because it is more than 230. So any number is more than 70 is okay. All are same.
Okay, sir. Thank you very much.
So let me share my screen. Then so now in between, let me take attendance also sometimes. So my screen is visible.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So so today's outline is actually means we looked at the quick look HPC train and study requirement, and then HPC course. Some people have requested what are the books and content, and then we'll move towards the very basic today classes and yesterday classes. It is story based. Story based means we will not move towards formulae. Okay, so story means no analytical thing. So then slowly we'll move towards means core part and mm, analytic part. So whenever I say story means actually no formulae or no analysis. So today also we'll go with story. Okay. So if you look at our paramesan, so you have heard about this name paramesan, I think so. And if you look at paramesans, HPC system, whenever we set up a HPC system, we call as data center. And this site looks, let me change the pointer, laser pointer. So this site, it is actually means what are the outer look of actually paramesans. If you enter to our data center, Institute IITG data center, it looks like this. Okay, there is a very big space. There are many racks. Okay, there are many racks, and each rack there are many rack servers are there. And whenever you say rack server is one node. Okay, rack server is one node. Means one node means it is we can count as one PC or laptop. Okay, node is you can assume as a one machine. Okay, and in a HPC system there are many such machines. Okay, the whole data center or HPC system divided into many racks. Okay, and many rack server in a rack, and one rack server is actually multi-core means node. Okay, multi-core node. So in that way you can see. And if you look at paramesans, our IITG paramesans, who have actually these are the specifications. We don't need to go detail, but still there are 4 login node. So 2 for general CPU computing, 1 for GPU computing, 1 for MIC. This is Intel GPU computing. Intel not GPU, but as GNP computing. Then 1 head management node and 1 management node. So this is actually one redundant node and management node. There are 4 plus 2, 6, and there are 126 general compute node, 4 high memory compute nodes, 16 GPU compute node, 16 make compute node. Total actually 130 plus 32. So 126 plus 4 plus 16 plus 16. So 130 plus 32 is 162 plus these are the extra nodes. So 4 plus 2. So 162 plus 4, total 166 node. And in network, there are InfiniBand network storage. You have 150 terabyte of high throughput scratch storage, then home storage and long-term data storage. There are for archival. This is for the storage server will be there. So there is network area storage server. And if you look at the HPC trend, then if you look at this thing, so there are many GPU node, and each node is actually what I can say having 24 cores. Okay, so 22 or 24 cores. So HPC system, whole HPC system we can program using MPI program, and nodes are multi-core, so we can program a node using OpenMP or OpenCL or CUDA programming, because each node, if you look at each node, there are 16 GPU node. So suppose you have machines and you have a GPU installed, then you can program using OpenCL or CUDA. Okay, so GPU node can be programmed. MIG program also, MIG is actually Intel Phi card, so that have also OpenMP and MPI programming can run on MIG. And after that, each core, so in a node there may be 22 core, and each core may be multi-threaded. So back with the vector instructions, and 4 is to out of order pipeline, then multi-level cache, and we can use a programming model like vectorized code or OpenMP code to do programming for a single inside a core. We want to take benefit of multi-threaded thing. Anyhow, in a node, so OpenMP can be recommended. Suppose you have a machine, you can single machines, then you can use OpenMP program or even MPA program also. But you have a multiple nodes, multiple different computers and connected through network, then it is always we recommend or always we go for MPA programming. MPA is completely distributed programming, message passing interface. And in this course, first we looked at some architecture specific little bit very high level. Then we'll move towards C++ optimization methods. What are the standard optimization methods we can look at? OpenMP, then simulations, cache optimization code that we looked at. Then this is the programming part. Okay, particularly OpenMP model, isolated model, and MPA. We looked at very high level initial 6-7 lectures. Okay. Then if we look at the course structure wise, so half part. So before mid semester, HPC, architecture, programming, code optimization. These are the first 1/4. Then this is scheduling, energy efficiency, power efficiency. This will be covered in the first half before mid semester. And second half we have cloud computing, mobile cloud, fog, edge, and IoT. So this is second part. And the book textbook. So particularly Introduction to High Performance Computing for Scientists and Engineer by Hager. So this is from this book we will cover some initial part. Okay, so particularly code optimizations part, or some kind of memory models. Okay, so memory intensity model, compute intensity model, and we'll have many user manuals and recent papers. Let's revisit the. Let's look at the multiprocessor. We'll revisit again. So during the course. And modern days, almost all computing systems are multi-core. So in your PC, we have actually Intel i7, i3, i5, i7, all are multi-core. Gen processor. Then this one is actually Qualcomm Snapdragon processor. So if you look at it, have actually hexagon DSP, sensor core. Then it have camera interface, display interface, location interface. This CPU is maybe a dual core, hexa-core or octa-core. Then we have actually separate hardware for security services, particularly encryption and decryptions. Then we have a separate codec for audio, video, and gestures. And for 4G or 5G or connectivity, we have separate hardware. So if you look at our mobile, so we have actually means that SoC have actually a lot of things. So it have GPU, it have DSP, it have a sensor core, you have actually display interface, camera interface, image processor. So a lot of things are there in mobile. So these are heterogeneous core, and heterogeneous core it actually really perform very nicely. So that's why in particularly mobile domain, because of this power and energy efficiency and with compact area, so we want to perform the things very quickly. So heterogeneous things are recommendable, and people go for recommended. All particularly associate guys, they go for heterogeneous systems. And this one is actually NVIDIA GPU card. This is Intel Phi Coprocessor. So Intel Phi Coprocessor, this is a small tiny core, but it have actually what I can say, around 72 core, and each core is 4 thread, so total around 300 threaded processor we will see. And you can write MPI program or OpenMP program on top of this. So very high level. So this in GPU we have nowadays around 5,000 or 6,000 or 10,000 small cores you will get. So, but this GPU core, if you look at size of this GPU and size of this Intel Phi Coprocessor, both looks actually similar size. So if you put actually 10,000 core here, and if you put 72 core, so the number of core will be here bigger, little bit bigger. But i7 and i5 we have actually big jumbo core, but numbers are less. So sometimes more numbers is also beneficial, and sometimes small number, bigger core are beneficial. So, but in SoC domain nowadays, people are changing to means some smaller cores, some bigger cores, some medium cores, kind of mixing all the things. But these are we cannot change the configurations, but what comes with that based on our applications, what we require based on that we should go. And this is 64 core Telera architecture. This was experimental architecture. This didn't come out to the market. And if you look at SoC examples, so what are the manufacturer of SoC? Do you want to know? Anyone can say from student sides? Mobile SoC manufacturers, system on chip.
Sir, Qualcomm.
This is Qualcomm. Qualcomm
Sir,
Snapdragon.
MediaTek,
MediaTek. Any other?
Samsung.
Samsung Exynos. Then
Apple are also making their own.
Apple also makes. And then one more.
Snapdragon.
There are 5. Clearly, there are 5 industry leaders. So I'll show you that 5. Okay. So if you look at in mobile SoC example, it is heterogeneous. Okay. Different hardware for different purpose, and it is very efficient in terms of performance, also energy. So one can argue that if you put a 16 core processor or 32 core processor, why you are going for heterogeneous? But sometimes what happens, if you are doing a specific work, specific guy can do very nicely. So that's why in mobile SoC they put different what I can say hardware. Okay, hardware block, particularly oscillator for different purpose. So this is hexagon DSP, that is ISP image signal processor. Qualcomm Spectra 250 image signal processor. This is the CPU. This is audio processor. Then have system memory. Then security processor. And this is visual processing processor at near GPU. Okay, and this is actually for modem and Wi-Fi. They have actually separate hardware. So it can be done with actually your 16 core or 32 core, but they go for actually heterogeneous thing, so that it can be done very efficiently in terms of both power and energy. So all the things in a single chip they do. That's why we call it actually SoC. So if you look at the motherboard, so earlier days PC motherboard. So we used to put separate GPU card, separate audio card, separate memory, separate security card. Everything we used to do separate. But in SoC, everything comes into a one chip. And this mobile manufacturer, this is the funny thing. So this Oppo, Vivo, or what is Realme, or many companies, they do actually mobile manufacturing. So what they do, they actually get the mobile SoC, okay, and they get different components. So they get different camera components, battery components. Then they get actually speaker or microphones. They have fingerprint sensor, antenna, then display, and they club all the things, design the external wrapper, then test on OS, and then they sell it. So particularly mobile manufacturing, just in our India also we have this Micromax, then Lava. So they also do similar kind of things. So they get mobile SoC, okay, and they get all components and make and plug in and they assemble it. They're actually, we can say they're branded assembler. Okay, almost this is not applicable to mobile system, but it is applicable to almost all bigger manufacturer, car manufacturer, or whatever, Hyundai, Maruti, they also do same thing. So they get the engine or tire, then windshield, different component from different sources, and they assemble and they guarantee the product. Okay, so all bigger companies, they are jugaad actually, essentially jugaad. So this mobile SoC, this major companies are essentially jugaad, but some companies they do their own. So particularly Samsung, Apple, and Huawei. So they are actually, they manufacture their own SoC, and most of the component they try to manufacture. So not like when, so just like Apple, they don't manufacture camera sensor, they don't manufacture display, but they get from other sources, but they try to manufacture their mobile SoC. This is a major part. Okay. So Samsung manufacture memory, Samsung manufacture camera sensor, Samsung manufacture LCD display or all touchscreen display. LG manufacture a touchscreen display for Apple also. So this is actually all are a kind of jugaad. And if you look at the multi-core ARM SoC, so these are the 5 particularly industry leaders. So Apple, Qualcomm, Samsung, Huawei, and MediaTek. If you look at Qualcomm and MediaTek, they don't manufacture phone. Okay, they manufacture phone SoC. Okay, so but Apple, Samsung, and Huawei, they manufacture SoC. Also, they manufacture. They are in business of manufacturing mobile phone also. So they are end-to-end kind of things. Okay. So Apple A15, so near M1X or M2. So they have actually 3 GHz core, 2 GHz core, 8 core, and all accelerator, heterogeneous accelerator, neural engine, GPU, then image processor, all the things combined and they make SoC. So whatever earlier previous slides I saw. So almost all SoC have similar kind of components. Okay. So processor may be different, some component may be different. Okay. Qualcomm Snapdragon, they have actually 1 Koryo, the 2.8 gigahertz, 3 A78, and 4 A55. So this is actually all are, even processor core are heterogeneous because processor consume most of the power. So and performance we get out of this processor, general performance, then they change a variety of processors. So here hexa core or octa core. So 3 gigahertz and 4. This is this high frequency one they call as actually performance core, and low frequency one they call as energy core or efficiency core. Okay, so performance core means a high frequency. Efficient core means it is energy efficient core. So it will run at a lower frequency, do a suitable for low end job, but most of the time we do low end job. High end job actually we do for less amount of time. So that's why whenever you require, go for high frequency, otherwise switch to low frequency so that it will be energy efficient. So Qualcomm Snapdragon also they have actually 1 2.8 gigahertz, 3 2.4 gigahertz, A78. A78 little bit bigger core. Okay. So and A55, 55 series are smaller series. So these are smaller core with smaller frequencies. That's why they are energy efficient. So similarly, Samsung also have, they have A4 A73, 4 A53, and they have a Mali 72 and all component. This is GPU component. This is 5G component. Other codecs. So Huawei also similar kind of things. So they have one very performance core. So 3 gigahertz A77, 2.5 gigahertz, then very efficient core, 4 efficient core. So everywhere you will see the heterogeneity in even processing system, not only the accelerated system and processing system also. And for multi-core SoC, you have the benchmarking. So based on what kind of memory interface they have, what kind of other interface may have, means based on this LCD interface. Suppose your LCD is very slow, you cannot play a high-end actually game. So that 3D mark may not result you good. Okay, but N2 Geekbench may show you good result. Okay, so based on other component, it depends. But this N2 9, Geekbench 5, these are the benchmarking things we do for mobile platform. So these things are very story oriented. Everyone knows these things. So we don't need to go in detail about this. So and these are actually all A15, then SD 888, then high silicon 900, 9000, Dimensity 1200. These are all modern what I can say SoC, which are used for our high end phones, recent high end phones, particularly Apple iPhone 13, then Qualcomm 888. It is used for this OnePlus high end mobile. So Huawei. P mobile, so high silicon 9000 they use. MediaTek 1200 also, it is very 5G mobile, almost recent. So these things are all what I can say fun to know. So this is general knowledge kind of thing. But still in our course we may require. And why this multi-core? Almost everywhere they are going for multi-core. So SoC are actually heterogeneous and multi-core. And why we are going for multi-core? So multi-core is a saturation of single processor performance. So if you simply increase the frequency, earlier they used to do simply increase the frequency to get higher performance. But as speed limits, we cannot cross more than 4 gigahertz or 5 gigahertz because it is ultimate point. Because So whenever you are increasing frequency, your actually size also get reduces. So if you reduce the size up to some point, you can reduce, not more than that. And another thing is power consumption is proportional to cube of frequency. So P is actually, if you look at the P is equal to half CP square F, and V is proportional to F. So in processor or any circuit, electronic circuit, voltage and frequency are there proportional. We can have actually some discrete set of voltage and frequency. Discrete set of voltage and frequency. Suppose 5 volt, suppose 3 gigahertz, then 4 volt, 2 gigahertz, then 2 volt, 1.5 gigahertz. Some voltage and frequency set. So discrete set of voltage frequency pair, we say. Okay. So every processor can have this kind of things. Discrete set of voltage frequency pair, and power is proportional to cube of frequency. Okay. And in single processor, so almost earlier research say that branch prediction accuracy goes up to 90%, 95%. L1 cache hit miss rate is actually more than 80%, and ILP explored by any processor is up to 8. We cannot go more than. What is ILP? It is instruction level parallelism. In single processor, we have instruction level parallelism. And another important thing is thread level or data level parallelism need to explore if you go for multiprocessor. And in general, this is actually nowadays more popular, and we go for multiprocessor for using or exploiting the thread level parallelism of almost all applications. Nowadays, almost all applications are actually very highly parallel. So if you look at CNN, DNN are actually very good for parallel processing. Okay, they have a lot of parallelism. So even GPU can take huge benefit from the CNN, DNN code, not only multiprocessor. And if you look at the power over scheduling, so nowadays power is actually more focused. So as compared to simple. Yeah. Hello. If you have any questions?
Yes, sir. Excuse me, sir. Am I audible?
Yeah, audible.
Yes, sir. I am asking that can we say like multi-core and multi-processor are these two things same?
Look at whenever you say at high level, both look same. Okay, but whenever we multi-computer means it is separate computer. Multi-processor means multi-processor and multi-core are almost same. Core almost similar, you can say. We don't differentiate between them. But whenever if you go to market, so whenever you say processor, then they will say one chip. Okay, so in a rack server, so we have multi-processor means they say that two processor chip can be fit, and inside a processor there may be many cores. Okay, so in rack server or high-end you can say machines, workstations, so it can support two processor. Whenever we say two processor, when it says two processor chip, a processor chip means two i7 chip or two Xeon chip it can support. Okay, and two i7 means each i7 have actually 8 cores inside.
Okay, sir. But can we have like can one process run in more than one core like that way? If we
Yeah, so one process can run on multi-core. Okay, so it can be run. So, but it need to be multi-threaded. Then only it can run multi-core.
okay, sir.
Otherwise, by default, process we say is single core. Okay, but if it is multi-threaded process, then it can run on multi-core.
Okay, sir. Thank you.
How well it determines. So, in general, all thread get cloned into process, and it run as multi-process. Some systems, some operating system they do.
Sir, like some bigger edge, sir, it is important that every HPC should run a single OS. Like, could different OS run on different cores and communicate with each other through MPIs?
Yeah, that is possible. So
Okay,
that is
so
possible. But in general, people don't do that thing.
okay.
So to manage very nicely, so they actually installed SAM OS in every system, and there will be
Okay.
common method so that they will get a common thing.
So
So in our system also they use SAND OS.
uh, so sir, like in Paramishan, there is a single OS or OS for every processor.
No, there is OS for every person, but all OS are SAM OS.
Okay.
All machines have SAM OS.
Okay.
So in general, it is very good for management. Okay, and another thing is we need to look at not only OS, we need to look at the file system also. Okay, because it need to access by many other. Suppose a file is shared, so that file need to be accessed by multiple machines, and it need to be same kind of file systems. Suppose you are using Windows, then it will use NTFS, but in Linux system, it will use actually other kind of extended systems. So in Linux file system is different as compared to Windows file system. Solaris file system. So that's why they use not only the same OS, same version of OS also. So rid of many problems. Okay, so let's look at the power hour scheduling. So if you look at power consumption is proportional to frequency cube. So power is equal to half CBF square. Okay, and V is proportional to F. So in general, we have a voltage frequency pair. And running a processor at 3 GHz will consume around 27 times higher power as compared to the running at 1 GHz. It is not actually 27 times, but the difference is huge. So running a processor at 3 GHz will consume around 27 times, because proportionality will say it is not 1. I'm not saying 1. Okay, but proportionality may be small number or maybe higher number, but it is the difference is huge. Okay, so P is proportional to means F cube, P is equal to K F cube. K may not be 1, but it is actually the difference is huge. So running a 3 GHz processor will consume in terms of what I can say order, or K is equal to 1 order term. So it is 27 times I'm saying. So 27 times higher as compared to the running the same processor at 1 GHz. So energy consumption will be actually it is, if you look at running conditions, means energy consumption is time into power consumptions. So P into T. So running a task at F and F by 3, assume 3 GHz, 1 GHz. So this is running at energy consumption at F and energy consumptions at, so this is E. So this is, let me write. So this one is actually E, not F. So energy consumption at F3. So energy consumption at F is KF cube T. So this is a power consumption part, and this is actually time part. And if you energy run at frequency F by 3, then this one is actually energy consumption part, but time will increase, because time will increase 3 times. So that's why we have T into 3, and total overall actually F cube T by 9. So this is a F by 3 cube, and this is T into 3, and this will be 9 times energy efficient. So running at 1 GHz is 9 times energy efficient as compared to running the processor at 3 GHz. So for if you have 2 times slower but 4 times energy efficient if you run at half frequency. So in that way, actually means all energy efficient system, they try to run the frequency at run the processor at lower frequency, but more number of processor. They go for more number of processor. Okay, so if time permits, reduce the frequency, so to save energy. Okay, and if time have enough slack before deadline, reduce the frequency. So that's the standard rule. And if you have only one processor, then you need to run at high speed, because you need to perform. But you have multiple processor, okay, multiple cores, then and your application have parallelism, then you can run at lower speed. So that will not only be means power efficient, I mean performance efficient, that is power efficient also. And why multi-core? So we are going for a very high level again. So high performance application specific ASIC. Application specific ASIC means these are exact hardware. Okay, so hardware for specific applications. So IC for specific applications. So whenever you design, have you ever seen calculator? Hello from student side, calculator.
Yes,
sir.
Yes,
So
sir.
our regular calculator. So I don't have. So a regular calculator also they use specific application specific IC. Okay. So they have very small memory. They have they don't have actually proper processor, but they have actually proper ICs. So whenever you press 5 into 3, immediately display result 15. But whenever you write a C program for that, so what you need to do? You need to write some has include std.h, then main, in main, then write code input output, do scanf, then do the operation, then printf, then we get the result. Okay, so there are a lot of things involved whenever you're going for processing. Okay, so complete processing. But whenever you are having a application specific IC means, so it takes inputs, multiple inputs, and it produces the result exactly direct output. So kind of what you can say 3 into 5. So directly it will result 15. So what it is, there is a multiplier. Okay, there is a multiplier, and you are giving input 3, you are giving input 5, and getting direct result 15. So here we don't have actually what I can say compilations, running on processor, getting instructions, fetching instructions, then memory, this thing, display, that kind of things are not there. So this input port is directly connected to the keyboard, output is directly connected to the display. Okay, so this is called application specific ICs. So application specific ICs, it is for specific purpose and it is designed for only one purpose. So earlier days, have you seen this Symbian OS, very old Nokia mobile? So earlier they used to have only one small SoC and very small things it can do. But nowadays this SoC are much bigger, MP SoC are much bigger, the Qualcomm SoC are much bigger. So earlier days the Qualcomm SoC are very small and they didn't have actually proper processing component. All are based on application specific ICs. And application specific are high performance, lower than power, just like oscillator. And but complexity of ASIC is very high nowadays because of many components getting in. Qualcomm Snapdragon, this 880 processor, you cannot make it as ASIC. So it need to be programmable. It is otherwise it will not be flexible also. So nowadays this 50 MP USD videos, GPS camera inside mobile handset, and it cannot be possible. So that's why this ASIC is gone. And VLSI technology, particularly chip manufacturing technology, offering a very high integration density, and it is very earlier, more layers says that double the transistor every 26 months for past 3 decades. So exponential growth in number of transistors in an IC. So we can put more number of transistor. It translates to more number of processor in a single ICs. And another thing is many applications are highly parallel. I already told you this CNN, DNN. There are many media applications. Okay, CMD applications. There are many applications are highly parallel. Even whatever we think also, it is highly parallel. At the time of presenting to you, I'm seeing a screen. I am doing my hand gestures. I'm thinking something. Okay, there are many things going on in parallel. So by default, nature is parallel. Okay, so in many simulations or many real life simulations, many things done and get in parallel. But parallel thing we try to convert into serial whenever you try to read in algorithm course. Okay, so regular real algorithm, we try to formulate the parallel things into a single serial version and then try to solve. But by default, the nature is parallel. Okay, so many applications are highly parallel, and by nature is parallel. We can take benefit of all kind of parallelism, instruction level, data level, and thread level in multi-core. And multi-core processor are flexible, programmable, and high performance. We can take benefit of parallelism, whatever I said, and it likely to made a low cost, high performance, effective solutions. So suppose you are designing a new processor and you are trying to improve the performance. Every time you need to go for newer technology to improve the performance. But if you are going for a multiprocessor, then you can replicate the things. So smaller, earlier design processor, you can replicate and create a multiprocessor. So just like in Qualcomm Snapdragon or even this Apple A15. So they are using same ARM processor. So slightly variations, A55, A73, then A74, A78. There are 4 or 5 different variations, not more many variations, but they are combining very nicely and to get the very good efficient solutions. If they only go for only one processor, single processor, and they try to get the different solutions for different power, then they may not get. Okay. So multiprocessor is likely to be cost and power effective solutions. And multiprocessor are flexible, programmable, high performance, and processor are programmable as compared to ASICs, flexible in terms of ASIC and high performance than single processor. So whenever I say high performance, better than single processor. Not it is not as compared to the ASIC. ASIC means application specific ASIC, but it is still better than the single processor. So have you understood this term? So high performance and single processor means it is not high performance as compared to ASIC. ASIC are actually application specific ICs. So these have input and directly output. It have all the things computed in hardware. So just like calculator, it is very fast. And another important thing is multiprocessor are likely to be cost and power effective solutions. Why? The main reason is share a lot of resources, and it get design time also. It have actually many things get replicated. So replications allow you to do the duplications. So once you design, you can copy paste and get a means a lot of things done in less time. So power effective means it share a lot of means resources. So in multi-core, it share a lot of resources. Personal room is costlier than dormitory, similar persons. And you cannot allocate a bungalow to each student. It will be too costly. Hostel room with share facility is sufficient, and it will be a cheaper solutions. So this is a general example. So why multiprocessor are cheaper and cost-effective solutions? Okay, so in general, based on requirement, you try to do. And whenever you are sharing something means it will be cheaper, but it comes with some other thing like interference and other things. But still, it is much cheaper. And not only require very high frequency to run, but it can go with very low frequency because we have multi-core. Multi-core means we can run at low frequency and get higher performance. And lot of replications make it easy to manage and cost-effective design for multi-core. So that's why multi-core is popular. Another thing is what are the difficulty comes. So whenever say multi-core is likely to give cost and power effective solution, but it comes with some difficulty also. So what kind of difficulty you face in your hostel? Hello? Hello? Am I audible?
Sir, not in the hostel for 2 years.
Not in the hostel for 2 years. So in general, so whenever there is share things, so share thing have some issues. So sharing things means, so we have issues with
Sorry,
interference, simply interference.
Yes,
Interference. Whenever sharing them, so that means interference. Okay, interference means someone want to go to bathroom and someone have already occupied. Suppose number of bathroom are less than. There will be a queue. Okay, so interference is first thing. So multiprocessor are likely to be cost and power effective solution, but it come with other things also because it share a lot of resources. Okay, personal room is costlier than dormitory. So sharing resources arise many other problems. So whenever you share something, so we have this critical section problem. What is critical section problem? At a time, share resource cannot be used by multiple person. Just like means a toilet, only one person can go. You need to be in queue. So someone need to lock and unlock. Okay. So critical section problem is actually means whenever there is share resources and multiple people try to access. Okay. And this is not the non-shareable resource. Multiple people can means access. Then we need to have proper mechanism, particularly critical section mechanism. So in OS course we have read this thing. So any sharing of resources, it have this thing. Also not only that thing, interference also. Even if so there are suppose messes have many tables, but many people cannot go and sit there. So it has some capacity. Okay, and sometimes you need to be in queue. Okay, so one processor interferes with others. And another problem is coherence problem. So shared data at all places should be same. So in particular, whenever you are going for multiprocessor, then we need to run actually multi-threaded program. Okay, multi-threaded program. And suppose a data X. Okay, coherence means shared data at all places should be same. Suppose there are 5 places, 5 processor. We have a multi-threaded program, and X is shared by all the processor. Then value of X should be same at all the places. So that is the standard. It should be same at all the places. Then only you can say it's coherent. Coherent means it should be same at all the places. Suppose I am giving a very layman examples. So layman example is suppose you have changed your mobile number. Okay, and your mobile number is shared by many people. You have given to many people, and you have changed your mobile number. Then what you will do? So because now your mobile number is not coherent, you have changed your thing, but your mobile number is available with many of your friends. That is not coherent mobile number. So what you need to do, you need to call whoever wants have your mobile number, give a broadcast message that whoever having my mobile number, please change to this new number. That is one way. Otherwise, you send to some selected people, selected friends or selected your family members, and then they will change. And if other people want to know, that they will call to your relative or they will call to your close people, and they will get the number, new number. So there are clearly two ways to handle this problem. That is called coherence problem. In multiprocessor also have similar kind of issues. So whenever the shared data is modified by many peoples, okay, then every instant of times, the value of shared data must be we need to ensure that it need to be same at all the places wherever it is available. That is called coherence. Okay, and what is consistency? So in our algorithm course, most of the time we design actually serial algorithm. Okay, and whenever you try to implement something serially, and that same thing we want to parallelize and run on multi-core, then what do we expect? So whatever the serial code, whatever you got the result, so we should get similar result in multiprocessor code also. If we run on multi-core also, we should get similar kind of result, not exactly same result. Okay, so order should be similar to serial. So you got my point. So you have any doubt about consistency and coherence? What is consistency? Consistency means it need to preserve the serial order. That is called consistency.
Sir, I have another doubt. Here in the first line, you have written multi-processor. So are you referring multi-core processor with multi-core, or is it multi-processor?
So we can think of any, but it is very high level still. So we can say multi-threaded processing or multi-core processing or multi-processor processing. All three.
Okay.
Sir, what is ROB?
Reorder buffer. This is reorder buffer. That's whatever the parallel code need to correspond to some serial versions. So serial C code we parallelized to some threaded code, and we want to test whether the parallel code is giving correct result or not. So that means it is consistent with serial code or not. So whenever you parallelize something, so we test with our serial code whether this parallel version of my program. Suppose you have a C program, and we converted into multi-threaded program using pthread or OpenMP or something. So in OpenMP, we are getting different result. Then it is not good. It needs to be correspond to a sequential result. But it needs to be high performance, but similar result. You got my point? What is critical sections? What is coherence? What is consistency? And another most important thing is, so whenever there are multiple processors, so there will be interference. So we need to share the things differently. Interference means suppose we have a 1,000-seated hostel. Okay, 1,000-seated hostel, and there are suppose 4 wings are there in hostel, and each wings have actually 5 bathrooms. Okay, so each wing have separate bathroom. You assume that each wings have actually 250 people, and they will have 5 share bathroom or 10 share bathroom. Total 40 and 10 bathroom per wing. So per wing you have actually 250 people. And this interference, this 250 people, so they assume that they will use this 10 bathroom. But sometime what happens, this in a particular wing, so number of people may be less, 100 people. So 10 bathroom per 100 people, and other wings, so 250 people, 10 bathroom per 250 people. So this interference sometimes happens, and one will interference with others. Some people they use for longer time. Some people they don't use for longer time. So based on that, if you can divide the people, then interference will be much lesser. Okay, so you must have seen so many people what they do. If they go to mess, so they usually talk for longer time, and they spend half an hour or 1 hour in mess. And some people they simply go and eat and come back. So different people have different behavior. Similarly, different applications have a different behavior on their memory access. Suppose memory is shared or cache is shared, and one application is accessing the memory very frequently. Okay, and very densely it is accessing the cache and memory, and other applications is not accessing. But if both got the same preference, okay, then what will happen? Suppose both have some quota. So both can access 5 times per second. Then those who are accessing very less, so they are free. They are every time whenever they get, they will get. But those who are required more, so they will suffer. Even if other guy is not using, so they will suffer because of this quota. But quota will, suppose one guy, if there is no quota, then what will happen? If there is no quota, then what will happen? This guys, so who is using much, he will not give chance to other guy. So how to handle the interference? So share efficiently using some policies. So that is the, in multiprocessor, this is another difficulty we have. We need to handle. It is this difficulty one. In terms of this is actually architectural and this kind of from prospects. Another prospect is many applications are highly parallel. We can take benefit of parallelism, but most of the code are write sequential code. So who will extract parallelism from applications? And till now there is no successful auto parallelism tool till date. But nowadays, good news is CNN, DNN, Python library is quite successful in GPU domain, but not for all domain.
Sir,
Okay,
what
so,
is CNN, DNN?
So this is CNN means convolutional neural network and deep neural network. So in ML, machine learning course, we generally read about convolutional neural network and deep neural network. And we write Python code for this machine learning code. Is it clear? Those who are in fourth year, they must be knowing. So means BTech fourth year. Some people are from third year, I think so. That's why they may not know this CNN, DNN business. And most of the times, most of the coder write sequential code, and who will extract parallelism from applications? Suppose you write C code and some compiler automatically generates the parallel code, then it's good. But sometimes you cannot trust the compiler whether it generates good code or not. Until now, almost no successful autopilotions tool till date. And another difficulty is task scheduling in multiprocessor. Deterministic task scheduling on multiprocessor with more than 2 processor is NP-complete problem. So simple examples. Suppose this is 4 taxes and 3 processor, and you have many variety of solutions. Suppose this is one solutions. So this is one solution. This is one solutions. This is another solutions. So 4 taxes and 3 processor, and this number of solution is exponential. Which solution is good? So that is very difficult to say. So we need to test all the solutions, then only you can say. And very simple example is suppose you have 8 taxes and execution time 2, 4, 8, 5, 6, 4, 3, and 20. So how many? 8 taxes. Okay, and need to execute on 2 processor non-preemptively. Need to be executed non-preemptively on 2 processor P1 and P2, so that overall execution time is minimized. Suppose you want to solve this problem. So how we do? So divide 8 taxes into 2 subset with difference of their sum is minimized. So create means subset 2 subsets. This is I'm first 4 taxes I'm taking and next 4 taxes I'm taking. So 2 subset and sum them. So 2 plus 4 6, 6 plus 8 is 14 plus 5 is 19, and this side is 10 plus 3 13 plus 23. This is 33. So this difference we want to minimize, 33 minus 19. So we want to divide in this 8 taxes into 2 set so that some difference of their sum is minimized. And if you look at these things, suppose n taxes and 2 processor. So this problem is made to a subset sum problem, a standard subset problem of any algorithm. So is this clear? Hello, from the student side. And And do you know
Yes,
what
sir.
is subset problem is? It is very difficult problem. If it is 2, then it is 2 set problem. If it is 3, then it is NP complete problem. But SAM problem, if you say it is non-preemptively you can execute onto process, then it is very easy. Suppose SAM problem, instead of this thing non-preemptively, if I say this task can be run preemptively, means we can divide the task, then this problem is very easy problem. So what you can do, all n taxes, you sum it, sum of all ti and divide by 2 and allocate to one process. So because it is divisible, so preemptible, then you can simply divide and allocate to one process. This is very easy. If it is preemptive is allowed, preemption is allowed. If this preemption is not allowed, then problem is very difficult problem. So what are the difficulty? First difficulty is, so we need to solve this critical section coherence consistency problem, interference problem. Second one is, who will parallelize this thing? Even if we parallelize, then sibling is very difficult problem. So in multi-core, means definitely high performance computing system is, we need to deal with multi-core processing. We need to deal with task scheduling. We need to deal with optimization thing, but we need to look at from these prospects. Okay, this difficulties. And this finishes our very high level thing. Okay, so a story based kind of thing. But now we'll move towards our main purpose, that is fundamental of serial code optimizations. So here, instead of going to multi-core immediately, why not to start with actually serial code optimizations? So given the C code or Python code, how to optimize the code first for high performance. So basic optimizations criteria. So where you are losing the performance. So that is basically what you can say. Whenever you're reading a high performance course, high performance computing course, where you are losing the performance and from the code, from coding point of view. Anyhow, if you are using a very good algorithm, that is different. So first thing is, if you look at my first thing, so if you look at this slides, so programmer have choice of algorithm, intelligent coding. Okay, then what intelligent coding is who is doing the coding. Okay, so intelligent, if you do the coding, then you'll get very good performance. If you use very good choice of algorithm, so if you are using, instead of n square algorithm, you use n log n algorithm, then definitely it will be, performance will be good. Okay, so in terms of performance and compiler level also, we can do a lot of things we can optimize, and many things are, if you know the how it optimize, we can write the code in that way so that the compiler can optimize very nicely. And inside processor, we can do many kind of hardware level optimization to do the improving the performance. And some of the things are uncontrollable, the OS workload. Suppose you are trying to test your performance of your code on some machines, and sometimes you get 1 second, sometimes you get 3 seconds, sometimes you get 4 seconds, because it is sometimes you are not environment you cannot control. Suppose you have written a code and you have submitted your code to some other machines, and other machines depend on loads. It will report different times. If your own machines and you are not using any other kind of what I can say workload, and you are testing your things, your work or your code independently and on single machines without running external workload or other workload, if you are testing, that's fine. Otherwise, if you are running on a share machines or some places, then we don't have some control. Okay, suppose in OS also, some background process, some internal process also runs. Suppose whenever you are running your code, some internal process or background process may be running. Okay, so that you cannot say. So even if we say performance is good, but we cannot report very crisp and clearly. Is this clear? So we'll next class we'll go for actually serial code optimizations. Next classes we'll go for serial code optimizations. If you have any questions, then whenever you are doing serial code optimizations, so there are some standard optimizations, machine independent. What machines you are using, still you can use this optimization. machine independent optimizations. So just like code of motions, reduction in strength, common sub-expression elevation. These are the some common optimizations things we should always use. Then some machine dependent optimizations, just like loop unrolling or enabling instruction level parallelism. Suppose you are using a processor with actually high level instruction level parallelism, try to enable that thing. And identifying the bottleneck. We'll discuss many tools related to this. And identifying performance bottleneck means, so identifying the hotspots. So you have written a 10,000 line code and you are running the 10,000 line code on some processor and it is taking 2 hours time. And you figure out that this 2 hour, out of this 2 hour, so time, so 90% or 95% of time is spent on the 3 or 4 line of code. Then you try to means looked at the 3 line of code out of this 10,000 line very carefully to improve the performance. Okay, so very simplistic example I am giving. So if you look at the context switching code, so in our PC system, okay, or any OS, context switching code, it do every means milliseconds do the context switching, and context switching code get executed very frequently in OS. If someone write even if very 2 or 3 very redundant instruction is there in context switch code, then it will degrade the performance. So that's why people write which code is very bottleneck code or hotspot code, that get optimized very carefully to improve the performance. So it is what I can say, naturally everyone will do that thing. If some code is getting executed very frequently, it's better to optimize that code very carefully. Okay, so that thing will do. So, and then if you know the your code and branch structure on your processor, then you can do very good optimizations. If you have cache structure of your processor, if you know, then you can do very good optimization of your code. And some advice also you can take from the compilers. Once you run the things, the profiling system can give you some kind of input that restructure this part of code or do this kind of thing, some kind of advice it can give. Hello from student side, do you have any questions? Any doubts about this? Hello?
Sir, but how we are saying of, let's say, optimizing the code instead of, let's say, without knowing the algorithm, the code is
No.
on.
Once you written the code, so what I told is actually, so there are 3-4 level of optimization. So if you look at programmer choice, so choice of algorithm and intelligent coding. Once you do the coding, during the coding, so you can actually do the optimizations. So algorithm is first level one.
Sir, what if
Yes,
the
sir.
optimization itself takes more time?
No, optimization means it will not take more time. So because you write code in a such a that it will be produce a optimized code. Means I'll give you many examples. So next classes we have actually many examples how to optimize the code. So next classes we'll see many optimization techniques. So which will not take more time. Actually, at the time of coding, you can see the code and transform the code on your own. And sometimes compiler internally do transform, but always you cannot trust the compiler. If you can do at your programmer end or programming time, so why not to do at programming time?
Okay.
Hello,
Yeah.
sir. Is it possible for you to share the slides with us?
Yeah, I'm sharing the slides.
No, I mean in the Teams.
Teams, I have already shared the last lecture slides.
Okay, sir.
So every time I'll share. Light will be said.
Okay, sir.
If there is no question, then you can stop recording and you can stop the class.